Welcome, those who've just joined. You haven't missed anything yet, and you're in the right place. I'm going to begin now. Welcome again. My name is Ben Dudley. I am the director of Mainers for Clean Energy Jobs. We are a coalition of businesses, business associations, labor unions, trade associations, and noted environmental leaders in the state of Maine. And we organized about 3 years ago to be advocates in support of the New England Clean Energy Connect because of its potential both to do a lot of economic good for the state of Maine, but also to put us in a leadership position when it comes to addressing the crisis of climate change. I'm delighted to welcome our speakers here this morning, as well as all of you. Each of our speakers is going to speak for about 20 minutes, and then at the conclusion of the second presentation, we'll take questions from all of you. You just type your questions in the chat area, and I will ask our presenters the questions. I will take the questions in the order that I receive them. Before beginning our introductions, I just want to make an editorial comment that over the last 3 years, as concerns the New England Clean Energy Connect, I think we've all noticed efforts by those who oppose it for their own reasons, efforts by them to reject or distort and sometimes even try to dismantle the structures and institutions that serve us in establishing fact and finding truth. And today's webinar is about, through the institution of science and the empirical method, to determine what the truth is about clean energy from Quebec. And our first presenter is Dr. Paul Stancioff, who is a just retired professor of physics at the University of Maine, Farmington. Dr. Stancioff and his spouse, Cynthia, jointly write a regular column on energy matters called Energy Matters that regularly appears in the Lewiston Sun Journal online and is printed in several local weeklies. Paul, we're delighted to welcome you here, and I hand the lead over to you.
Thank you, Ben, for that introduction. I'm going to get my PowerPoint here started here so that you can all see it. Okay, I just want to make sure everybody sees
yes
the right thing. Okay, get my own screen straightened out here. Okay, so this all started, the reason I think that Ben invited me here is because one of our columns was titled, "Is Hydro Really Dirtier Than Coal?" And I'm here today to kind of talk about how we got to this particular article. And I'm going to get to this later, but it was triggered by a letter to the editor by Jonathan Carter, who was opposing the power line and said something about it being dirtier than coal. But I'm going to get back to this because I just want to do a tiny bit more about how we got to the point of doing these articles. I've been teaching at UMF for 34 years until 2 weeks ago. And one course that I've taught for over 20 years is about energy. It's called Physics, Energy, and the Environment. And my focus in this course has always been getting students to understand more about the numbers associated with energy, because you can't really make any good decisions without the numbers. And in the process, I've concluded that the general public also needs that kind of an education. And so last year, Cynthia and I started writing this column that Ben mentioned. It's available, as he said, on the Sun Journal online, Franklin Journal if you're in Farmington, the Norway Advertiser, Democrat, and Bethel Citizen. We try to be really about practical matters, like what is a heat pump? How does it work? Some physics. What is the payback time? Why would you want to get a heat pump? What are the financials on it? How does it affect your carbon footprint? Very little too controversial there. Here's another one. People concerned about how much land is being taken up by solar panels. Well, it turns out that even if we used all of our power from solar in Maine, it would take up a fraction, like less than 10% of our existing farmland. And of course, you wouldn't use farmland for that necessarily anyway. Here's one that we wrote recently that did have some pushback, a little more controversial. We got feedback from the pellet industry concerned about our article, and not a positive feedback, but it was good, healthy feedback. And then this article that got us here today, question, is hydro really dirtier than coal? So before I continue, I do think it's important for me to put forth these caveats. First, I have no association with or vested interest in Hydro-Québec or Central Maine Power. We are at our columns for one reason. Our single biggest concern is climate change, period. Also, I want to point out that I'm concerned in the bigger picture about hydropower use around the globe. And some reasons for that are that there really is limited appropriate topography to increase the amount of hydro that's available. When you flood large areas for relatively low power density, you do produce greenhouse gases, and it's in fact what gives hydro a bad name. There are some other environmental reasons. You know, you have to weigh our options on things. Issues with fish or silting of the rivers. There is room for hydro to grow, but it's very important that any developers in the process that they choose locations and design their facilities so that greenhouse emissions are taken into consideration. And then there other renewables have really a lot more room for growth than hydro. But as I'll point out later, hydro can play a very important role. But in the end, hydro only has so much potential for growth around the world. I've heard numbers somewhere in the vicinity of 50% growth. Some may say higher, some say lower. But we need a lot more growth in renewables than that. And so that can only come from other renewables, such as wind and solar. We need maybe a factor of 20 because we need to not just replace our energy, electrical energy with renewables or from fossils, but we need to electrify way more things. It's not going to be enough just to replace the total power we use from electricity now with renewables. We need to increase it because we need to have enough to consider increased public transportation, electric transportation, both public and private transportation, building usage, heat pumps, induction ovens, stoves. And to do all that, we need a more robust and modernized grid. It needs to be a smart grid, inverter friendly, and it will need basically storage, and batteries and hydro can act as storage for that. The other reason I'm concerned specifically here is about the referendum question, which, among other things, could make it really, really difficult for any major power line projects to actually get done. If a power line, for example, crosses any leased public land, there could be 12 senators that could stop this for political reasons or for whatever reasons. So that's sort of my bigger picture. So let me get on to how we got to the hydropower article that we published. As I said earlier, it was triggered by this letter from Jonathan Carter. A couple of quotes from his letter. An area about the size of Connecticut is no longer pulling carbon out of the atmosphere on an ongoing basis. And the other quote, one report out of MIT has estimated that some of the reservoirs are emitting more carbon than a coal-fired power plant. And he goes on a little bit about methane, 80 times more impacting than CO2. Well, this is how my brain works. Just for fun, I said, well, how big is Connecticut compared to Quebec? And so I drew this rectangle in here. This rectangle highlighted now in red is about the size of Connecticut in Quebec right here. Well, you know, it's a little less than 1% of the area of the province of Quebec. If you look at Connecticut. I just thought I'd take an example of Connecticut, and you cut out a rectangle about the same area in percentage, in fractional area, a little less than 1%, it would look like that. This is how my brain works. Turns out that the total area of reservoirs, of man-made reservoirs in Connecticut is almost this big. And it's like 30 something square miles instead of 40 something square miles. So I like to put things in perspective, and I really don't like when people use numbers like the size of Connecticut basically in a dramatic way to make things seem bigger than they are, basically sensationalize it. So anyway, that's not particularly important. What's more important was the second statement. The report estimating that some reservoirs do put out more carbon than a coal-fired power plant. So I emailed Jonathan Carter. I'm acquainted with him. I have long acquaintance with Jonathan. And I asked him what MIT study he was referring to, and he told me that he was referring to a peer-reviewed work by Bradford Hager, who's an earth sciences professor at MIT, also has a home in Mercer, Maine, near me. Jonathan told me he had not reviewed that work, but he'd read about it in the Portland Press Herald. So what I did then, of course, was try to locate this peer-reviewed work out of MIT. What I found, though, was what Professor Hager had testified against the power line in December of 2019 at Army Corps of Engineers, but it was not his peer-reviewed work. He took some numbers from some publications, which I subsequently looked at. But the irony of it is that I did find an MIT study relating to the power line. And it is a study that was started out as a working paper from a group at MIT called the Center for Energy and Environmental Policy Research, CEEPR. And they're talking about how the role that Canadian hydropower would play in decarbonizing our electricity sector in the Northeast. Since this working paper, this has actually been published in a peer-reviewed journal, which talks about the role of hydropower reservoirs in deep decarbonization. I want to point out that it refers specifically to reservoirs and not just run-of-the-river power. And the reason is that in order to decarbonize, we need a lot of renewable power in New England, and that means wind and solar for the most part. But of course, the issue with wind and solar is intermittency and variation in power output as opposed to demand-based power output. And the role that hydropower and batteries can play is huge because basically the reservoirs in Quebec play the role of a deep cycle battery for the power system of New England. And in fact, their conclusion, I'm not going to get into this paper any more than that, but the conclusion from this paper is that the value of hydro reservoirs is shown to derive from their balancing of renewable intermittency at multiple time scales. So that means short-term, variation from renewables, but also long-term. You get a long period of no wind or whatever, that they're like a deep cycle battery. Incidentally, this requires the power line to be a two-way line, and I've been told that it's in the design of this DC power line that it will be a two-way power line. DC power lines require a little more effort to be two-way than an AC line, but it's being built in. So let me get to the article. I'm getting a little behind on time here. What does it mean to be dirtier than coal? Well, coal puts out pollutants. Other than CO2 and methane, it puts out particulates, it puts out sulfur dioxide and nitrogen oxides, mercury and other toxins. And from what I've read, you get some sources say that it can account possibly for 10 million excess deaths per year from coal plant pollution, burning coal. Obviously, that doesn't apply to hydro. Hydro doesn't emit particulates or sulfur dioxide. But ignoring the excess deaths issue, ignore that. The specific comparison that we really need to look at is how much greenhouse gas is produced for a given amount of energy produced. that's how typically this is measured for all electricity generation sources. And the measure we use is how many grams of CO2 equivalent is produced for every kilowatt hour of electricity generated. And so I just use the grams per kilowatt hour. It's grams of CO2 equivalent. And that equivalent, we use the word equivalent because it counts for the relative warming potential of methane, which is the other greenhouse gas that is produced both by gas, natural gas plants, and by hydro reservoirs. So what does this mean? And how do you compare one energy source to another? Well, here's a table with some values. Look at the center column here, because that gives the median values for all these things. This also gives it sort of upper and lower ranges, so those are debatable as well. And you can see the coal is the worst, and then you have biomass, if it's co-fired with coal. I'm not sure exactly what that means compared to biomass dedicated, but you can see that natural gas is around half, maybe a little more than half of what coal produces. And for, what am I cursor? These things, they don't have very much variation up and down. Then you get down into the renewables and nuclear, and they're very, very low in comparison. So, down, 10 times smaller than gas, and smaller than that yet. But I want to, it's important to look at hydropower specifically, because if you look at this, you look at the minimum, the median, and the max, it has by far the largest range. The range is huge, from almost 0 to 2,200 grams per kilowatt hour. So that means potentially a hydropower station can produce 2.5 times as much greenhouse gas as a coal-fired power plant. But look at the median. Median is 24. Now, this data is old and probably needs to be updated. I think it's from before 2014, but I'm not positive about that. But that's a starting point. So I started looking into this, and I've been reading some papers, found these papers, particularly the one by Scherer and Pfister in 2016. And I found, yes, some reservoirs are high methane and CO2 emitters. These papers get into a lot of detail. There's quite a lot of variation from one reservoir to another, as I'm reading in here. And hold on a second, I gotta fix my notes here. And these results are really based on statistical modeling. They're not, most of these results are not based on field measurements. They're based on sort of theoretical outputs based on temperature and age of the reservoir, among other things. This paper talks about the impact over time, how a hydro reservoir has pretty high greenhouse gas outputs over the first few years. Alain's going to talk more about this in his presentation, so I'm not going to get into it too much. So this is kind of what I was finding. And then finally, I found the thing that Jonathan was talking about, which was Hager's testimony was not to the PUC. I have an error in my slide here. It was to the Army Corps of Engineers. And this is what he presented. These numbers are grams per kilowatt hour, the same unit that I use. And you can see these numbers that he's highlighted. These are his highlights, not mine. And they're pretty large. This is like a gas-fired power plant. This is more than a coal plant.
Paul, sorry to interrupt, but these are all hydroelectric reservoirs in Quebec. Is that correct?
Yeah, I'm sorry. I meant to say that. These are all hydro plants. Thank you, Ben. These are all hydro plants in the Hydro-Québec purview that Professor Hager used in his testimony. And some of these numbers look really large. I'm going to get back to this later, that there's some real problems. But you can see, I think, that this is the Scherer and Pfister using one output, this is the Scherer and Pfister using a different output, you get very different results. And by output, I mean you're taking the greenhouse gas output and dividing it by the power output of the power plant. If the power output of the power plant is not the correct value, you're going to get an incorrect value for the ratio. And Hager used the smallest power output he could find for that, and I'll tell you later, is really not the right value. There's another issue about this that has to do with Lagrange 2A as well. I'll mention in a little bit. Sorry, I got to find my notes again here. Okay, moving on. From what I could find, looking at the Scherer and Pfister paper, and I looked at a bunch of the results that the Scherer and Pfister paper had. What I could find, the Hydro-Québec reservoirs from their data looked like it had about 170 grams per kilowatt hour. And by the way, this did not include run-of-the-river stations, which are ones that don't impound a large area, surface area of water. And so they tend to be much lower in greenhouse gas outputs. The output has to do with the surface area. But it surprised me how high this was, even though it is still a lot less than any fossil fuel source. And this is when I first contacted somebody at CMP. I had a contact information for Thorne Dickinson. And I called him, and he put me in touch with Ben, our host today, and with Alain Aspect, Alain Tremblay, sorry, who's speaking after me. And also they connected me with the paper by Annie Levasseur and other people, including Alain. And it was at this point, I looked at this paper, and this looked like the first paper I could find, a peer-reviewed paper that actually had results of greenhouse gases from reservoirs based on actual extensive field measurements. And Alain is going to talk a little more about this, but seeing this and seeing their results, I felt like we had enough information to write the article. I'm sorry I'm going over time here, Ben, but I'll be done in a few minutes. I'm going to give the conclusions to the article, and then I'm going to just talk a little bit about the response to it.
You take your time.
All right, thank you. So just quickly over what we concluded in our article, and feel free to read it. I don't know if Ben's made that available. But we concluded, yes, hydropower does emit greenhouse gases. People are often concerned about how much greenhouse gas is produced when you pour concrete, and it is an issue on a worldwide basis for construction. But in the case of dam construction, the energy that goes into construction of the dam and CO2 output of concrete is really tiny in comparison to its entire life cycle analysis. And you can account for with about 2 grams of CO2 equivalent per kilowatt hour of the electricity produced over the life cycle of the dam. Most of the of the greenhouse gases is from the surface of the reservoir in the flooded area and also downstream. But and again, these are the conclusions that we really wanted to communicate to the public. The amount of greenhouse gases vary hugely from one facility to another. Some reservoirs do produce high greenhouse gases per unit of energy produced, but oftentimes that's because the energy value is small. You're dividing a greenhouse gas value divided by an energy output. If that reservoir happens to produce little energy for whatever reason, maybe it's not just producing energy anymore, you have a denominator here in a ratio, which is a really small number. It gives you a very large number, even though the contribution overall can be very small. And then we point out the results from the Levasseur paper, which is that they concluded that the greenhouse gas output from all the Hydro-Québec facilities averages to about 35 grams per kilowatt hour, which is down there with all the other renewables. A little bit higher than what that table I showed you earlier, but not very much. And just a little bit about the follow-up. Brad Hager, I had found in another article, newspaper article, he was quoted as conceding, if you will, that it might be 175 grams per kilowatt hour. But he wrote me in response to our article. And I just want to quickly go over some of his comments in my rebuttals to it. He was unhappy with that Hydro-Québec used 17 grams per kilowatt hour as the output of the greenhouse gas output of their power. I pointed out that I don't think that Hydro-Québec uses that value anymore. They're more likely to quote the Levasseur value, which is still pretty good. He still thinks it's higher than even his 175 grams. And I did also point out he wanted to know where he'd made these errors. And I wanted to just point this out quickly. That table I showed you earlier had the Bourassa station and the Legrand 2A station. And he used a value of 5.2 terawatt hours per year to calculate the result. But Bourassa generates over 30 terawatt hours per year on average from what I get from Hydro-Québec. I'm assuming they're not lying to me. And Legrand 2A produces over 11 terawatt hours. Together, they produce more than 42 terawatt hours per year. Instead of dividing by 42, he divided by 5.2. Well, we know 7th grade arithmetic, that means his number is between 7 and 8 times too large for that value. So that's what I pointed out. In the article, I pointed out he'd made an error and he was wondering where it was. I don't know if it was his error or if it was an error in Scherer and Pfister that he was using. He also claimed that it's impossible to attain a low average when some of the reservoirs emit 10 to 100 times of that. And I point out, of course, it's possible. If you have a large number of facilities taken into an average and they're weighted appropriately, then you can. If you take two reservoirs that one produces 1,170 grams per kilowatt hour, this is a sort of a simplistic example, but I have two reservoirs. One produces 1,170 grams, the other one produces 30 grams per kilowatt hour. If you take the average of those two numbers, you get 600. Does that mean the average is that the correct value? Well, no, it depends on how much each one produces. If reservoir 1 produces a very small amount of energy and reservoir 2 produces a lot of energy, you have to take total greenhouse gases divided by the total energy. You can't just average these two numbers. So it is possible. And some of those outliers in greenhouse gas emissions don't contribute very much just because it is, they do not, we pointed out one particular reservoir that has a high greenhouse gas per kilowatt hour value, but doesn't produce much energy. So he also claimed that the Vassell paper didn't properly account for ice cover, but Alain will talk about that. And Annie Vassell, I emailed her and she assured me that this is not the case. And when he quotes his best estimate at 170 grams per kilowatt hour, he really thinks it's higher and that it's about half that of a natural gas facility. But I also pointed out to him that only the best natural gas facilities have greenhouse gases less than 400 grams per kilowatt hour. Most of them are higher. And that doesn't take into account methane leakage, which is a real problem in the distribution of natural gas. You get something like 2.3% of the natural gas leaks. And if you take that into account, it actually ends up in an equivalent greenhouse gas output of about 700 grams per kilowatt hour. I'm still waiting to hear back from Professor Hager, and I will try to keep people informed on that interaction. I'm sorry I've gone over so long, but that pretty much concludes my presentation. Thank you.
Thank you, Paul. And to those of you who joined after we started, we will be taking questions after Alain Tremblay's presentation. So sit tight, there will be an opportunity for questions. Our next presenter is Alain Tremblay, who holds a PhD in environmental science and is senior environmental advisor on aquatic ecosystems for Hydro-Québec. He is extensively published in peer-reviewed journals on the subject of environmental impacts of hydroelectric reservoirs in boreal climates. And I'm delighted to welcome Alain back. Alain, the floor is yours.
Thank you, Ben. Let me share my presentation. Can you hear me properly, Ben?
Yes, I can.
All right. So thanks. Well, I'm going to present some of the studies that were done in Quebec with different universities and different research center on emission from reservoirs. So we'll see that we are really far from anything related to thermal power plants, or particularly coal. And this is science what I'm going to present. So some facts about what we do in Quebec. So it's not really a recent issue for us. We've been documenting emission of greenhouse gases from over the last 25 years or so. We have documented those emissions over more than 31 reservoirs in Quebec, many lakes and rivers, to see the differences between reservoir and lakes and see how they varies over time. We have documented the three major gases which are related to flooding of reservoir: CO2, methane or CH4, and of course N2O, but I won't talk about that because this is a negligible part of the fluxes. I'll focus more on CO2 and methane today. We also had the opportunity to do two major world premiere in Quebec, which is the East Main 1 net emissions and Romaine, where we have generated tons of information because of really well detailed studies on greenhouse gases from those projects, which are the newest project that we have in Quebec. One thing you have to keep in mind, it's Hydro-Québec and the scientific community is changing over time as the information becomes available and methodology are more developed. And this is a good case here. In the 1990s, we were measuring fluxes at lakes or reservoir using floating chamber. So a good year, you had 200-300 measurements. But now, since the automated system and the development of automated chamber for soils of eddy covariance, we're more in the order of 20 to 40,000 measurements per year. So it's totally different. As the technology is available, we put it to use, and we are trying to document better what's going on in terms of our installation. So science has evolved over years, and we have also changed using different technology. We have synthesized that information, a few years ago. How do we understand the dynamic of greenhouse gases from reservoirs? So this is the next few slides, or basically what do we understand so far from those reservoirs? First, you have to, this is a natural lakes anywhere in the world. And what you're going to have, it's going to have exchange of CO2 or carbon from the atmosphere to the lake as the wind blows in. So there's an exchange between the atmosphere and the water. You will have a lot of carbons going to be fixed by the terrestrial ecosystem. To create vegetation, you need to absorb CO2 from the atmosphere. Part of that carbon will go on the ground, and then part of it will be transported to the lakes or the reservoir through streams or rivers, either in the particulate forms or basically dissolved. But the end result is that you have a lot of carbon going to the system, more than the system can fix. So either carbon fixed through fish flesh or vegetation growing in the lake. The result is you have more carbon going in than it can be fixed by the system. So you're saturated in CO2. So more CO2 in the water than in the air. System try to reach an equilibrium. Sorry. So you're going to have fluxes that going out of the water body. And that's about 90% of the lakes around the world that behaves like that. So more carbon going in than they can fix. So basically they are emitting CO2. So what's happening when you create a reservoir? Well, first you have the major impact. It's you have created, you flood some terrestrial ecosystem. So you're going to have the same, when creating a reservoir, you still have the same thing going on at this interface atmosphere and water. So some exchange between atmosphere and the water. You will have the same order of magnitude of carbon coming from the watershed as with the river and the streams. So those sources are still there with the reservoir, but with the creation of reservoir, you have additional sources of carbon to the system. One of them, it's as we generate electricity, the water volume, water level of the reservoir will change according to the electricity generation. And that, with the effect of waves and wind, will erode part of the organic matter that's being present there. And that organic carbon will be used by the bacteria within the system. The other source is that the vegetation flooded, or part of the vegetation. We're not talking about the trunk here. We're talking about the leaves or the lichens or the easy degradable material that is on the soil. And that would have been decomposed anyways, just it's a bit accelerated within the reservoir after flooding. So you have additional sources. So you're super saturated in CO2 in the water column compared to a lake, and therefore higher concentration in the water, higher fluxes that's going to go out of the system. That's happening everywhere in the world, lakes or reservoir, but the magnitude and the duration and time will depend, and it's temperature related. So it's really warmer is the system, higher will be the decomposition or bacterial activity, and probably also the emission of greenhouse gases. What's happening after a couple of years? Well, you still have those exchange with the air. You still have the inputs from the watershed, but organic matter which is the soil in boreal ecosystem Quebec, you got about 6 to 8 inches thick. So it's easy to not degrade, but erode them. And therefore you end up as like the picture that there's no more organic matter present in the drawdown area. So no more organic matter present, well, no more methane or CO2 that can be produced. So that's no sources from the creation of the reservoir. Within a period of 5 to 10 years, it's already gone. So we don't count that anymore. The second one, it's the decomposition of organic matter. Well, usually from what we've been measuring, it's the easy degradable organic matter is already gone within a period of 5 to 10, maybe 15 years, depending where you are. And then therefore, after 10, 15 years, these additional sources present at the beginning of the flooding are highly decreased or inexistent after 10, 15 years. So the concentration of CO2, because of the decrease of those sources, the concentration is much lower than at the beginning, and therefore you end up with fluxes at the surface of the reservoir, which are in the same order of magnitude, similar to those that we have in lakes. And of course, you have also the degassing that takes place all the time, but the concentration is decreasing as the water concentration or CO2 in the water in the reservoir decrease. So it's really related. So when we calculate how much greenhouse gases comes from a reservoir, we take into consideration all the pathways where the greenhouse gases are taking place. So one of them is the bubbling that's usually take place in shallow or warm, shallow area. Most of the biggest pathway in Quebec, it's really CO2 diffusion and some of the methane diffusion at the surface of the reservoir. And then you have the degassing as you take water, which is saturated in CO2 or methane, and then reach equilibrium downstream of that reservoir. But we put that into the reality of Quebec or Canada, where it's a cold country. So we have ice between 180 and 212 days per year. And when ice cap is present, diffusion or bubbling are considered zero. It doesn't mean that there's nothing going on in the reservoir, but there's no fluxes taking place at the surface of the reservoir because of the ice caps that seals the system. However, we do take into consideration, what's going on in the system as we measure the CO2 and methane and the water go into the turbine. So you can see what's going on when the ice caps forms. You have an increase and then a decrease in the spring. So we take
compensated for.
So we take into consideration all of those values on an annual basis. So when we do the mass balance, that's taken into consideration overall budget. The other consideration that we have to consider, it's the characteristics of the system. So physical and chemical characteristics of boreal system where it's colder. So when you have colder system, usually you can have a higher concentration of oxygen in the water. And when you decompose organic matter, and I'm repeating myself here, it's a natural phenomenon. You will favor the formation of CO2 when you have oxygen because it takes least energy to create CO2 when you decompose organic matter compared to if you do you create CH4. So in Quebec, because well-oxygenated waters and cold system, decomposition will favor CO2 instead of CH4, which it might be different in tropical area because low oxygen and a higher temperature. So Quebec, we are basically physically favoring the CO2 emissions over the methane. Another things that Hydro-Québec have done with this with many partners, it's to another world premiere. It's really to document East Maine 1 and La Romaine in terms of net emission. Net emission is really having a look at what's going on in terms of natural ecosystem, what the peatlands is fixing or emitting in terms of CO2 or methane. Same thing for forests, taking into consideration the forest fire. This is a very important part of the natural cycle of the forest and boreal ecosystem. And then when you have calculated and estimated the sink and the source of carbon and also those ecosystems, you put a reservoir on it, and then you see the difference between the natural ecosystem and the new system with the reservoir. And then we can determine the effect, the real effect of the reservoir on the emissions of greenhouse gases. That's what we've been done, and it's been published a decade ago with the East Maine 1 project. And the way we've done that, it's using different techniques to document the spatial and temporal variability of fluxes over time. So for 7 years in East Maine, and then we have started in Romaine in 2014, and it should go up to 2025 to get a really good information of data to calculate the natural or the net emissions from those systems. We've done that with East Maine 1. It's been published a decade ago, where this is the curve integrating all the natural fluxes as well as the reservoir effect. So what you have under the curve, it's really the net emissions. And you see that the reservoir effects is really taking place the first few years. After that, it's basically values really quite comparable to natural lakes. So there's an effect of the reservoir East Maine in terms of net emissions. If you use those results, which is a lot of data generated on the field, more than 250,000 of information generated, then we calculate in terms of kilowatt hour. You see that East Maine takes about 7 years to be much better than any natural gas combined cycle. So just by the science, we're far away from natural combined cycle. So for me, it's really difficult to see how we can compare hydropower in Quebec with coal, because the science is not there. We're much better in hydro compared to natural combined cycle. So with coal, I don't see the science supporting that from my point of view. So what we've done is, once we've generated that value on the field, the measurements on the field from terrestrial aquatic ecosystem. So all that science is used now by other researchers to do that life cycle assessment from construction, generating electricity, and all the way up to the delivering that energy to the client. And that was done, the latest version of that. So using the latest or the most advanced science, the best documented science we can get in Quebec, with the new protocol for the life cycle analysis. Lavasseur 2021 have done that analysis, taking the scientific information and put that into the life cycle analysis. And this is the results. You can see that hydropower from Quebec, it's 34, 35. It's quite comparable to other renewable in the area, but it's much lower than any thermal power plant based on science. There's other action that Paul already mentioned, that you can use the hydro to compensate for the intermittence of the other renewable, but the idea, it's not zero, but small emissions that we have from Quebec based on science. So this comparison of energy, as it's based on good science that we have not done by ourselves. It's been done, it's well documented, it's published in peer-reviewed scientific articles. It's available for the people for more than a decade. And it's been done in collaboration with different university and research center for many different things. One, to have quantification of the emissions, but also to understand those the process leading to those emissions. So we are able to explain why the emissions in Quebec are different than those from other area, because we don't only have the measurements, but also the processes leading to those emissions. So that number 35 is based on the best science that's possible. Quebec is the area in the world where we have the most information on greenhouse from reservoirs. So this is, in terms of science, that the best we can do to explain. And that 34, it's really based on very good science. So that's all I wanted to say on how it's documented. It's really based on science. I don't know if Ben, you want to jump on question, or you want to add something else before?
No, Alain, that was terrific. Thank you. And I think now's the time to go into our Q&A. And for those of you who haven't done this before, if you see at the bottom of your screen, you'll see a Q&A button and 2 dialog boxes over it as a symbol. You click on that and you can ask your questions there, or if you like, you can also ask them in the chat. I have received one question already, and Alain and Paul, you might want to speak to this as well. The question is, how many refereed papers does Professor Hager have on this subject? And to remind everybody, Bradford Hager is the professor at MIT who submitted public hearing testimony to the U.S. Army Corps of Engineers that made the case for Hydro-Quebec energy being as dirty as fossil fuels. And Paul mentioned Professor Hager in his presentation and the flaws in his research. But Paul, can you speak to how many refereed papers Professor Hager has on this subject?
I know. I really don't know. I know he does some work in carbon sequestration, but I haven't looked at that stuff. Specifically about this subject of greenhouse gases from hydropower. Again, I haven't found any of his work. His area of expertise is in other areas. I do know that he's doing some work with carbon sequestration, and I also know that he's as concerned about climate issues as we are. So I have to treat him with respect, because I get that. It's just that on this we happen to disagree. But I wish I could answer that question. I don't know. Maybe Alain, do you?
Well, we follow all the literature, scientific literature that comes out from anything related to lakes, reservoir thing, and I haven't seen anything coming out from Dr. Hager on that subject. So I'm not aware of any publication on that subject.
Okay, thank you. The next question we have is, will Hydro-Québec have to build new reservoirs to fulfill power commitments for the New England Clean Energy Connect? Does Hydro-Québec have excess capacity with existing reservoirs and with existing generator units within existing reservoirs? It's a little off our topic here, Alain, so I'm sorry to put you on the spot there.
Well, usually it's not me that answering those, but it's more the other teams that I work with. No, we don't have to build new dams for that. We already have excess of energy that could go to the US, and we are more than enough to export to those contracts. So we are not, our intention is not to build new projects. We already have the energy available to provide the energy for the Maine, so that we don't have to at the moment. Do we gonna have to build a reservoir in the future? We don't know, but there's nothing on the table right now for the next 10 years. So.
Thank you for that. And I will say that we have hosted a webinar on this topic, and when I get a moment, I will post the link to that in the chat window. So there is detailed information for you via video that I will share. The next question is, thank you both. Can you speak to the impact of longer, warmer summers and decreased ice cover in northern Quebec?
From reservoir, or this is well documented that climate change is taking place, and we are already seeing some of the effects of climate change on ice cover from, let's say, James Bay or the Arctics. We are actually having a project on research project with Université Laval on to see one aspect of that. It's how the ice cap will change over reservoirs over the years. That will benefit the greenhouse gases, but also benefits many other usage of the ice cover for the First Nation or any local community that are using the reservoir or lakes for transportation during winter with skidoos. So we are studying that. We know it's coming, that the ice cover change a little bit, but for that one published on James Bay and the Arctics, we know that the ice cover on James Bay usually the ice cover, it comes a bit later in the fall, and it's delayed by about 8 days in the fall, and it will go in the spring about 10 days earlier. So we're already seeing in the north some effect of climate change. But these are related to global change. They're not related to the Hydro-Québec facilities, because those are really big area. But this is something we are looking into for a reservoir to see how that's going to change the greenhouse gas dynamic or any usage of the reservoir because of the change of the ice cover.
Thank you, Alain. The next question we have is, I found Paul and Alain convincing. However, the No to any CEC website has so many other items. One, presented recently, expressed concern about the high power line, that no similar power line has ever been built, and that it is both a fire hazard and a microwave danger to wildlife. Again, this is probably beyond the expertise of our presenters. I don't want to prevent you from speaking to it, but I will say that these were matters considered by the Public Utilities Commission, and the PUC speaks to them in its order from, gosh, that was in May 2019. So these matters have been considered, and concerns about them have been essentially rejected after review. But perhaps this is a subject for a future webinar. Alain and Paul, I don't know if you want to speak to that at all.
Well, I don't know what other signals are going on the power line other than the power itself. But I have heard concerns about the electromagnetic fields from power lines. I mean, there's been issues about this for the last 30 or 40 years. People have been talking about it. There's a first-year physics problem of when you have a DC power line, a wire carrying DC power, it's a steady current, so you don't have the oscillating fields of an AC, 60 hertz AC. But it's a fun little physics project or first-year physics problem to calculate how strong the magnetic field is directly below the wire. If you know the power being carried, in this case 1200 megawatts, and if you know the voltage of 310,000, I think it is, you can calculate the current in the wire, and there's a simple rule for calculating the magnetic field. And directly below the wire, I calculated, I don't remember the value, but it's a little bit stronger than the Earth's natural magnetic field at that point. And as you get away from the wire, it drops off very quickly. So, once you get, I don't know, maybe 100 or 200 feet away from the wire, basically you could not detect the magnetic field of that wire over the Earth's compared to the Earth's. As far as microwaves, I don't know where the microwave would come from. I don't know if they're transmitting information down this wire. If it did, it would be really, really small variations in the voltage. That wouldn't, I don't know.
There is the fiber optic broadband line, but
that wouldn't be it.
Yeah. So
I can just add that.
As far as a fire hazard goes, I really have no idea, but that's not my purview.
Well, I just want to add on the new line. I mean, that type of line with the high voltage, it's been existing for decades in Quebec and many other places in the world. So that's not something new. So the science behind those transmission lines is well known.
I know that I've heard that I think it's in China somewhere. They have a 1,000 kilovolt line, a million volt line, almost or somewhere around a million, maybe 1,100,000 volts. That's a DC line that travels something like over 1,000 kilometers. And the reason for DC there is, of course, that it's extremely efficient compared to AC power lines. Over short distances, they're not worthwhile because of the extra overhead costs at conversion. But over longer distances, the DC power lines can be much more efficient, and that's the reason for it. They're also inherently less radiation from them.
I'll also mention that back in February of this year, essentially a who's who of the climate movement, NGOs in the United States, wrote to President Biden urging him to include climate components to his American Jobs Plan, including, and they emphasized, including incentives for the construction of high voltage transmission lines. So, I mean, there's clearly a strong movement among the leading environmental and climate organizations in the United States advocating for more high voltage transmission. The next question we have is, are any of the arguments suggesting Hydro-Quebec's greenhouse gas outputs are larger than Dr. Levasseur estimates based on an analysis of direct measurements?
No, Paul mentioned it, and I did mention that this is the average 34. This is the average for the whole Hydro-Québec generation fleet. Of course, for an average, the variation between 0 and some other are higher. But the results we have measured, it's within that range that Levasseur have published, because it's partly based on the science that been generated in Quebec and partly based on the GRES model to extrapolate to other reservoirs. So the science of direct measurements on the field is really supporting that number that Levasseur published. Keep in mind that this is the average for Quebec, and so this variation and within the province, but 35, it's the average.
And as I pointed out, the simple math is that if you have, there's a Gouin reservoir, which is used only to control, basically, I think it basically produces very little power, but it's been there for over 100 years and it's used as a recreational lake. And if you calculate the greenhouse gas per kilowatt hour from that reservoir, it turns out to be quite large. But that's because it's got a small power output. So you have a certain area which produces greenhouse gases, and you divide that by a small number. That small number, if you divided it, if you have a lake that produces no power, you'd get infinity. So in other words, it doesn't make sense when you have small powers to include it in your, it doesn't contribute much to the overall. It's just the arithmetic.
Well, that exhausts our question. I'll give people a moment or two. If you have a question, type away. Oh, we've got a partial question. Historically is all it says. Peter, is there more to your question?
I think I see it. I see Peter's question. Peter Duess. Historically, how did Quebec come to build an overcapacity for hydropower that they can now offer us stateside? Again, that's not for me.
Thank you. I have a glitch on mine. I couldn't see the full question.
Well, partly it's related to hydropower. The thing is, when we want to have a new project, it's we have to think about 15, 20 years ahead. So it's a partly planning of that. And when you have a project coming in operation, you will have a surplus on the short term, but that's going to be absorbed by the demand over the years. That's typical of any hydropower. When you build a project, it's 15, 20 years ahead. So when it comes into generate electricity, you have surplus, which is temporary until the demand will absorb the energy coming from that power station. So it's part of a hydropower development. You have to think many years ahead when you want to build that. At least this is the Quebec situation. With all the regulation and everything, it's at least 15, 20 years before you get anything in operation.
Well, that takes us exactly to 1 hour. I want to thank you both, Alain and Paul, for your work and for sharing it with us here today. And I want to thank everybody who joined us for the discussion. I have recorded it, and I will be sure to share it with you all as soon as the editing is complete. So thank you again, and stay tuned for our next webinar.
Thank you, Ben.
Thank you.
Have a great afternoon, everybody.